Hi. So yeah, I'm Armand. I'm now at Apple for like 2 months, and so all the work I'm presenting here is from my former employee, Meta. So yeah, nothing is from Apple here. It's only my new affiliation, and that's the only place where you see in the slide. So the topic of today is about democratizing large language model. I think it's a relatively important topic now, considering the revolution that has been recently seen in our field and has impacted the whole society, that I call here the ChatGPT revolution. I'm not going to define what ChatGPT and what it is. I think everybody has seen it, but it has shown that AI's methods only on text only can impact what we do in many fields, coding, for example, like automating how we code, creativity, writing stories, and so on, but also communication, helping us writing emails, helping people who are not necessarily familiar with, talking with institutions, how to, write for them, and so on. So it has a lot of potential impacts on society. So much that in terms of growth, this is one of the biggest launch in history. I don't know if we can really trust these numbers, but for the sake of having, for my talk, I shamelessly take them anyway. But it seems to be, I don't know what's causing that. Oh, people over there, okay. don't cross the beam, thanks. All right. But anyway, it's the biggest growth in history. They reached 100 million users in only 2 months, while it took for other companies like years to get to that number. That's pretty insane. They have been having a growth over the last few months. It's pretty impressive. But also, when you start to look at this graph, you can think, oh, wait, they are starting to plateau, and that was maybe only a hype. But the reality is that just schools was out, and so no students were using it anymore for their essays. So while that might be, just like, oh, it's fun, it's just, a glitch in their growth, it also shows that this model is being used like very seriously in our education systems. People are now, trusting these things to, write and learn. So we need to really have them perfect. And the problem here is that we also know that this type of things has tons of limitations. The biggest one that we are all aware of is the hallucinations, that basically, because it generates text, it can hallucinate things, facts, and so on. So if you are using them for your essays at school and so on, you may end up with something that is unverifiable and wrong. The second issue that I see with the current status of ChatGPT is that it has a monolithic view of the world. Like there is one company that has imposed their way of how it should be an AI, and we have to live with it. And that leads to the third problem that we are facing right now with the AI world, is that the technology behind ChatGPT is locked. It's owned by that company, and they do absolutely incredible things, but it doesn't open to all the things that we could do with it or analysis to improve them. So most of the talk, I'm going to talk about the last point, because it's called Democratizing Large Language Models, and how, as a community of researchers, we can try to offer alternatives there. The reason why I think it's important is because there are many sets of beliefs for many different communities, many different countries, and so on, and we would want to adapt this type of models to that, and so we cannot have just one closed model. We cannot study their behaviors, we cannot improve on them. It keeps the academia away from studying that absolutely incredible technology, and it doesn't allow us, for people who are more applied researchers, to develop new functionality on top of it if we are not at OpenAI. So kind of keep people away from, I think, one of the best things that happened in the recent years, and so that's a shame. I'm only here going to cover a part of the whole debate about open sourcing versus regulation. I think this goes way beyond that, because there is also of course, risk associated with open sourcing and democratizing things. And I encourage people to watch the debates between I mean, that was a video between the Senates with fantastic speaker in front of it. But let's say that for the sake of this talk, I think Hugging Face were the champion for me here. All right. So during this talk, what I'm going to talk about is I'm going to briefly introduce language models. So for people who are not familiar with it, hopefully by the end of the talk, and that's for me the most important, you will understand what is this technology, what is it doing. And then I will describe rapidly also one of these implementation, the Llama 1, which is an open source version of GPT-3, and a reproduction of Chinchilla, which was work done at DeepMind. And finally, I will discuss some of the future challenges when we want to bring these models to the next stage. All right, so if you talk about ChatGPT, you need to have a slide generated by ChatGPT, so I did that for this one. I hope this is the only one where I use that cheap trick. So here it is. I asked ChatGPT to give me the definition of a language model. Language modeling, because it was really, really painful to write it, and he gave me that, and it's really accurate. So basically, language modeling is the thing where you take a sequence of words, like with the first one, second one, third one, and so on, and you try to predict the probability of that sequence of words to be correct. So if a sentence has been seen regularly, it should have a high probability to exist, while a sentence which is just a set of random words put one after the other shouldn't have any probability. Then from that probability, that is, something that is correct English has high probability, something that is not English has low probability, you decompose it using the chain rule in a do I have a pointer? Oh yeah, wow. You can decompose this probability into probability of a word given its past. And so basically, this is what the whole language model is going to compute, is the probability of a word giving the previous words. So more concretely, let's say you have the beginning of a sentence like this one, the cat is drinking some. Your language model, what it's going to do is predict the probability of the next word that could happen in that sentence. The way it's doing that is by taking the words and transform them into vectors. So each word is associated with some vectors, then pass it through a big neural network, and for all the words in your vocabulary, they assign the probability to it. So they will assign high probability to words which are likely to appear just after, but they're also going to apply a probability over words which are very unlikely to appear, like this one. And usually this probability is non-zeros, which usually is one of the things that is causing the hallucination, is that you have a non-zero mass on unlikely thing. It's also what is allowing it to be creative, because it allows it to also have probability on words which are rarely appearing but still appearing. So that's the whole thing with language model. That's it. Like, that's what they do. They just predict the next word from a vocabulary based on the previous things with a big neural network. Okay. So how do you generate, once you have your neural network, now that you have learned that, predicting the next word, how do you generate from it? Well, that's pretty simple, because that's exactly what you have optimized for. So let's say you have the beginning of a sentence like the cat is, then you pass that through your neural network, like this little box, that gives you a probability of what should be the next word. So either the cat is sleeping, is annoying, is drinking, walking, again, tree with a small probability here. And you sample from that distribution. You just sample one of these words. Let's say drinking, not necessarily the first one, it depends on your sampling algorithm. Let's say this time you took the drinking one, these words, and that's it. Then you add it to your sentence, and you reproduce exactly the same process, where you basically have now this word drinking, apply compute the new distribution of the next word, sample from the distribution, and get the next word in the sentence. So you basically repeat that process of computing the probability of the next word, giving the past, and then sampling it, which is relatively costly, because each time you have to pass the thing through a whole neural network, but at the same time is incredibly simple and seems to be powerful. So there is something a bit magical here between the simplicity, the conceptual simplicity of what you are optimizing for and what you are resolving, and the ability that this type of models are able to the things that these models are able to do. So kind of magical things here that rarely happen usually in AI. All right, there is a bit more to it when you want now to make this work really in practice. Okay, it's very, very Swiss. All right, so there's a little more to it. Like it's just, and here I'm going to start getting a little bit of the details, like not too much, but of the things you need to know when you deal with language models, even if it's only to generate text. So the first things to know about these things, and here I'm first focusing on the things you need to know when you don't need to train them. So just, you have a language model, you want to play with it, you want to generate. There's a few things you need to know beyond how it works. The first one is that usually you tokenize your words into subwords units. So you never really take the whole vocabulary of English, let's say, and just predict on top of it. The reason for it is that if you go online and train a model on all the vocabulary, on all the English page online written by people and so on, you'll end up with more than 1 million words. So a vocabulary that is massive. It's not so much that English is a very rich language, but it's mostly that people misspell a lot, invent words, just, abbreviate a lot of things, capitalize, not capitalize. Like there's a lot of way people just mess with vocabulary, so you end up with a gigantic vocabulary. So instead, when you are working in this model, usually you work with another unit, which is a subunit, usually subword, that is basically your word has been split into subparts that are more frequent. And that helps to keep the vocabulary smaller. So this is to make things faster, to train better, and so on. So if you use one of these models and so on, don't be surprised if the number of steps it takes is not the same as the number of words in your sentence. It should be around 1.5 more or something like that. Can you, sorry, you're in front of the lights. Thank you. All right. So that's the first things to know. And also, these tokenizers are a bit of a piece of art. It's not easy, I think, to get the right one and so on. So usually it's the type of things you want to do once, but very well. And most of the people now are using something called sentence piece that is an incredible tool for doing that. Then if you are still only interested in generation, usually you have two parameters to tune, which are the temperature and the top P values. So usually if you, like, for example, if you take the llama code, you will have like your generation function here, and these two parameters here set to 0.8 here and 0.25. The temperature is basically the variance in your generation. Changing it will make it either only pick the most likely words or really kind of make the distribution more and more uniform. So that it gets closer and closer to something that just do random noise. So it's really the same as the temperature in physics and so on. And that allows you to reduce or augment hallucination depending on what you're looking for. So that's the first parameter that usually is very important to tune. And in most, and if you just take things out of the box and don't play with that, you may not always find the best performance you can get on the benchmark, depending on what the benchmark is optimizing for. The second one is top P, and this one is to reduce the problem of hallucination that I was describing before, which is that when you have a vocabulary, you always have a non-zero probability on rare words. On words that are very unlikely. So these things basically remove these words that are below a certain threshold or that are in the quantile. So top K is you just keep the top K words when you generate, and top P now it's that the mass is covered 0.95. So it's different definition of the same thing. But basically the goal is to remove words that really have no chance to appear. So these are the two parameters that usually you will need to work with when you do generation, and that's it. So basically you can take the code, apply generation, you just need to know that you are not quite working on the word level, and tune these two parameters, and you are set to go if you have a GPU. All right, so now the second part is how do you train the things? Basically, as for any AI things, it comes back to three components. First, the data. That's very important. The tools you have, so for AI, and these are relatively standard. Gradient optimization, neural networks, and all this. I'll get back to them, but this has been developed for a long time. And finally, a lot of compute. And I also go back to that and how much you need to train one of these models. So in terms of the data, usually for these models to work, you need a massive data set. You need like trillions of words. So usually that is done by downloading the whole internet or part of it through an archive called Common Crawl that is available to everyone. Then you need to select good data there because very clearly this model is just going to compress whatever you put in your pre-training data. So if the data is bad, your model is going to predict bad things. So really, if you keep in mind that if you put garbage in, you get garbage out, then you're good to go. You just need to apply that rule. Do I want my model to be exposed to that type of data? Do I want my model to generate this type of data? And so on and so on and so on. Like you have to have that conscious exercise while you select your data to train that. Finally, and that's also sometimes something that is a bit ignored, which is if you want a field to be covered, like if you want your model to be, let's say, good in low, you better train on low data. Like it's not going to invent stuff to field that it hasn't seen. So when you see a model and they are able to do stuff on this or that data, let's say, for example, ChatGPT able to write in the style of a certain author, you better bet that it was trained on data from that author. Like it's not going to hallucinate things to that level. Like you need data on what you want to do. So that's also very important. Fortunately for you, usually internet contains a lot of things and really a lot. So most likely what you want is already there. All right. So a concrete example of that is the training data we use for Llama. And I think the same was used in Llama 2. The first and biggest corpora was the CCNet corpora, which was a data set we extracted from a Common Crawl a few years ago, and that you can rebuild from our GitHub from this paper here. That basically take the whole Common Crawl and take a model that basically classifies if a page is close or not to Wikipedia. So that's our classifier to say if a page is good or if a page has a content that may be toxic or not, is how far it is to Wikipedia. And we basically keep only the pages that we feel the text is somewhat similar to Wikipedia. That still leads to, I think, overall we extracted more than 2 trillion or 3 trillion tokens with that thing, and we could have extracted way more. So you can use that, take all the Common Crawl dumps, and probably get to 10 trillion tokens easily. Then the second thing, of course, is to use Wikipedia. It's one of the best sources in terms of knowledge, especially in English. Stack Overflow is also amazing because it offers a lot of question answering on very high quality topics. And if you are careful in how you select your answers, and you pick, for example, always the best one. Sorry, you are in front of the. You are masking the. Thank you. What do I say? Yeah. You already get things that you see in ChatGPT that you have question and answers, so your base model kind of have already been exposed to that. So this type of behaviors has already been there. Archive allows you to know things about math, GitHub public repo for code, and so on. So basically from what we have tried here, you have already an idea of where the model is going to be good at and where it's going to be less good at, all right? Things that we didn't use, we don't see, you don't see the red arrow here, but it's what we didn't use. So what we didn't use are things like unfiltered Reddit, which has been used in the past because Reddit may sound like a good idea because it has a lot of conversational thing, so that it improves the conversationality of your bot, but if you don't filter it, and it's very hard to filter, I think, or at least in my experience, it's not that trivial, then you can end up with a lot of racist discussion and things like that, and it's really something that you don't want to have. Unfiltered command crawl is really bad as well because a lot of web pages are just generated, so you get a lot of boilerplate, a lot of things like that, and so your model is just going to learn to mimic bots online. And 4chan, obviously, should never be used unless you want to make a viral video, but else, like this type of things should never use in a model that you would want to use. Once you have this data, you need to pre-process them. And that's basically, so this is one slide in the presentation, but in reality, this is 99% of the work. Like coding the training of the language model and so on, is setting everything is 2 weeks of work. This is 6 months to maybe more if you really want to be to GPT-4. So that's where all the magic happen. And usually that's where there is the less detail in papers. Not because people want to obfuscate it, it's just because if you were to look at my code that I use when I pre-process things, even a week after I did it, I'm not completely sure what I did. Because it's really complex. The first things, but you can split it in a few stages. It's just each stage sometimes has to be repeated multiple times and so on. You have to look at the data, rechange a little bit of things. But anyway. So the first thing you need to do is deduplicate. You want to avoid things which are just exactly the same thing because it's probably just a copy of the same thing. It doesn't mean that the thing is that important. And if your model sees something more than the rest, it's just going to learn it as more likely than the rest. And so it's just going to repeat it far more, and so that's not very informative. So deduplication is very important, especially when you work online, because a lot of people are generating web page by just copying part of Wikipedia and so on and so on. So that is very important. The second one is removing boilerplate. It's a little bit for the same thing. If, like, let's say you work on GitHub, code data. Like most of code data has a boilerplate at the beginning that gives a license. Of the code, and they all are generated the same way. So now, if you just train your model to learn that, it's just going to learn to generate that boilerplate, and this is not great because again, it's something that is not very interesting for a bot to learn. So, and this can become very, very hard because now, let's say, for example, you want to tackle the problem of flow, so you may go for an archive like Freelo that is in the pile. And then you have all these flow documents, which are OCR of PDF of court session and so on. So now you have this boilerplate at the beginning, but has been processed through a PDF from different court places, and then OCR and so on. So completely messed up with 10 different boilerplates and so on. And so that's why usually you don't have the details, is because it's just like a nightmare to do that and end up being very hard to describe. But this is very important. You should also probably filter by language, because usually if you work with internet, you will have a lot of different languages, and if you're not interested in making multilingual models, then you will end up with a lot of your content that is not in the language you are targeting, and this is going to take capacity away from your models. So this is also something you want to do. And even if you want to do multilingual, it's still good to filter by language, so that you can rebalance your distribution more accurately. So this is usually the main things you have to do, but I think in general, the rule of thumb is if you want to use data, just look at the data, spend hours just going through it, see if there is any patterns, really bad things, like, you usually see people say, we remove any lines that is more than 1,000 characters long, and there is reason for it. It's like, because when you look at these lines, they are usually garbage, and why, I don't know, but so you need to come up with this type of rules. And there's no magic here. It's just looking at the data and processing that. It just takes time. And then training a model, check if you change something, if there's a huge drop because something has been not filtered. So it's the reality of this work. Okay, so once you have the right data and so on, then now really it's up to using your best AI tools. And here, really, most of the work has been done for us over the last few years. It's pretty amazing. We have an architecture that just works perfectly, the transformer, between the original one and the one we use in Llama in most things. There is a few tweaks, the way you encode the position. We use rope instead of the absolute one that was used in the original one and so on. But these are minor details. For the most part, like the transformer architecture is amazing. There's also the things between pre-norm and post-norm and this type of things. But most of it is just already there and it's perfect. It's perfect also because it's really well suited for GPUs. I think it's even better for TPUs, but I haven't tried that. But for GPUs, it's really nice. You can train your models with a lot of parameters easily. You just have to split them between GPUs. It's a great tool. And I'm not going to explain how it is. I think hopefully either you don't need to know because you are not going to really train these models, or if you are going to train these models, I don't have time here to go into the details that you need to understand the architecture. But anyway, so you take this transformer, create architecture between 7 billion and 65 billion parameters. We went for that range thanks to the paper from DeepMind called Chinchilla, who showed that these type of models were able to perform extremely well just by training them longer. Okay, so now basically the only thing that changed compared to my original style is that instead of having a random neural network here, now I have a transformer, but for the rest we did exactly what I described at the beginning, take word vectors, pass them through the transformer, then get your probability over the dictionary, and that's it, and just train that. That gives you a loss, and you just optimize for it. In terms of optimization, we use also standard tools that our optimization community has developed for us over the last few years. And are amazing. So the good old stochastic gradient descent, which is the whole reason why we are all here. There's an amazing tool that works surprisingly well. ADAMW, which allows for faster convergence, and also very importantly, the cosine learning rate schedule that turns out to be a very good way to learn rapidly models. It has drawbacks because you can restarting training is hard with that. I mean, once you get to the end of it, but this is basically the big tools. Gradient clipping, so that you don't have exploding gradients. This is also very common tools. And finally, use very large batch size. So up to 2 million tokens per batch. So you just have to have a lot of text you see at once when you are training it. At least that's what we found to be working very well. So once you've put that all together, like the transformer, you have the GPUs and so on, this is a type of nice curve you should see. Like you basically have your perplexity, which is or like your training loss, so how much you are able to predict the next word, basically. That is smoothly going down, like this one, like all of them. The shape of it, you have to be careful about the shape of it and also making any conclusion out of that because it's a cosine learning rates. So because of it, you will see like it's getting slightly less fast at the end, but a lot of it is just caused by the learning rate going to slowly to 10% of its original values. And so, and also if you look at the pattern of this one on 1 billion, you see it's exactly the same pattern as this one on 1.4 trillion, basically, just squeeze that. And this is really the learning rate. So it's the one takeaway from this type of graph is that the shape of it is so influenced by the optimization schedule you use, it's very hard to make any conclusion of, oh, it has overfit or not overfit just by looking at this curve. But they are still nice and going down, so that at least we should see when you're training them. All right. So now for the kind of say that the one part of the thing that kind of is the reason why, if it's that simple, like to train LLMs, why don't we have like billions, like different llamas and chinchillas up there, like trained by anyone? Well, the main reason is simply the compute. Training one of these models takes around 2,000 A100 for 3 weeks. So maybe, I mean, the code we use is probably not as optimized as Mosaic LLM code and so on, but still what we found is that this is a good order of magnitude of what you should expect. So if you don't have access to 2,000 A100 for three weeks, you cannot train one of these big models. If you want to go for 7 billion models, you can probably, you will be able to do it with 256 to 512 GPUs for a period of a week. But still, that is still a pretty significant compute that you will need. And that is just for one training. So that's also the thing to keep in mind is if you are reproducing as we do, even if you are reproducing as we do here, your final training is only one data point. You need to make sure that your data is good. For that, you need to do short trainings of like 300 billion tokens or these type of things. And so there is the additional cost of developing and debugging your code base and so on. And so there, you should probably count around 2,000 to 3,000 A100 for 6 months, I think is a good ballpark of what you should expect to use. And again, this is the numbers that we got from from Llama, which is really, again, just a reproduction of Chinchilla. So we knew what we had to do, and we knew what type of metric we were targeting. So now I imagine that developing Chinchilla probably took even more, and Chinchilla is an improvement over GPT-3, so GPT-3 took probably even more. So really depending on where you are between those who are pushing the limits of the technology to those who are improving it and to those who are reproducing it and so on, like your compute budget can have a factor of 10 to 100 there. So very, very hard it's the entry cost to be competitive in that space is pretty high. And so that's the reason, I think, one of the reasons why democratization of this model has been so hard. Hopefully, now that there has been papers like Chinchilla and Llama and so on out, I hope that the cost of reproducing and creating new models is going to be reduced, and so we will see more models coming out. So, but still, so okay. How much time do I have? 5. Okay, it should be good. Okay. So now, why are these models so good? Like, why are we all so excited? Like, I know ChatGPT is one thing, but really, like, why would I even try a base model and not just use ChatGPT? Is there something like that is fundamentally good with these models? I would say there is, yes, 2 things. The first one is they seem to generalize very, very well. Like, you give them any type of text, and they complete it remarkably well. So the example that I use usually to debug my model is this one, where I ask it to write a review for Yann LeCun last rap album. And usually it comes with this very long, it comes with this text like this one, very, very long, when you describe in details Yann LeCun, last article called Deep Learning, that is talking about, the topic of AI research, with loneliness in academia. It comes up with, lyrics here, and so on, and so on, and so on. So it's very, very good at inventing things, because obviously Yann LeCun never drop a rap album in the real life, to hallucinate things and make up stuff and creating new things. So this is really, and you get it from the base model without all the ChatGPT thing on top of it. So already you take that's a 7 billion model. So you just take that and you can generate tons of content easily. A consequence of it is that if you start playing with your prompts, you can start to make them do really fun stuff. One of the, I think, most powerful that was revealed in the GPT-3 papers is the few shot ability. Basically, you can give it a series of examples like this one, like car is voiture, car is chat, dog is, and then the model is going to predict chien. So it basically figures out very rapidly how to resolve a task. You can go even a step further. Like right now, I'm playing around with making prompts which are you are a set of human annotators that needs to, I don't know, write question to a chat bot and so on, and it will generate a ton of question and so on. And there were papers about that too. So not only you can do few shots to create this type of examples, but you can also kind of explain like what type of thing it is right now and make it then generate text based on that. And so, and this is really because you have seen so much different data online, so much different written content that you can make it simulate most of these contents relatively easily. All right. So just in for the last part and relatively short part of the talk, I'll discuss how you go from this base model, and very succinctly, to an AI assistant. So this is, so far what I've described is just a large language model. It's not the AI assistant like ChatGPT or Llama 2 or all these type of things. It's really the step before. What they have in common is that they are supposed to know everything. Like they have seen so much that they hopefully have the same knowledge as what you can find online. So they both are the same thing here. The main difference comes in how they perceive questions. In an LLM, they understand questions. So if you put a question or like put a pre-prompt, like say, hey, here is the answer that a chatbot answer to this question, then it would give you an answer. But it requires a little bit of engineering and so on. So it understands question, but doesn't necessarily always answer it and not necessarily in the way you want. While in this one, you kind of have that mode where it directly understands instruction. So it has been like fine-tuned to understand an instruction. So this is a big difference. The second big difference, and that's the alignment thing, is that because it has seen so much of internet, these LLMs, they have in them a lot of different tones, a lot of different opinions, a lot of different ways of describing the world. While usually in AI assistants, you probably want something a little more focused there. So this is the other element that people have been working on, which is this whole alignment thing. And usually these two things are done together. So basically, this is the fine-tuning or LHF part, where you simply make the model more and more better at its task of being an AI assistant. Now, one of the questions that for me is not clear is if this task, and here, like depending on the talk you see, you will have different intuition there, is does it improve the model? Like, does it really like unlock new abilities? Or is it simply like kind of surfacing some of the abilities that the model have seen during its training and make it focus on it? So that's not clear. If it's the first one, it means that basically this is a path to have like models which are able to do incredible stuff that we are not able to do now. Maybe solve math problems that we are not able to do. If it's the later, which is this one, then it means that basically what we have built is an amazing representation of the whole knowledge of humans online, but and what this is able to do is to create it and resurface it in the way we are interested in it, but it will never go beyond what it has seen with a bit of generalization there. The second element also that is, sorry, did I? Yeah. So this is, I think, one of the key questions and remaining things that is, if you are interested in that space, needs to be a bit answered. Like between these two things, what is going on, and depending on which team you are, it will define the type of method you are going to look for when you want to create an AI assistant and so on. The second element that is also really problematic is the toxicity of fairness in these models, because since you know everything, you also know toxic content, right? And the idea that sometimes you hear that, oh, it's easy, you just need to remove toxic text from your pre-training data and that will solve the problem, is, in my opinion, wrong, because you want your model to be exposed to toxic content. You need it to understand what is a toxic content. What you don't want is it to say toxic content. So there is here a problem that is really, non-trivial, I think, to solve, and it's getting worse because the more LLM knows, so the bigger it is, the more he understands toxic content, and so the more it is able to produce toxic content, and very good toxic content that is really harmful. And what the literature so far seems to say that the fine-tuning, gets you to some extent, but it's not enough. You will always be able to kind of make them generate some form of toxic content. So there is a fundamental problem here, and that I try a little bit to summarize in this way, which is that you want your LLMs to understand toxic content. So the reading part, if you want it to be able to read text and say, hey, this is toxic. As humans, we are able to hear someone saying racist comments and identifying it as racist. We want them to be exposed and being able to hear, but we don't want them to promote, so to talk and to say things. So these are two different abilities talking and hearing, and in the current decoder-only LLMs, we are kind of merging them together in our pre-training data. Like the data that they say they hear about, they feel they have to talk about it too. So the fact that we are mixing the two may be a fundamental flaw of the current methods and something that we may eventually need to revisit if we want to definitely resolve that problem. Or not, because there is also alternatives where we may, and there's an excellent paper actually by Anthropic on that, where you may want to change a little bit your pre-training text so that you identify when when a text is bad and you just need to hear, and when a text is good and you hear and talk at the same time. So anyway, so that is the conclusion of my talk. Hopefully by now you have a pretty good understanding of what is needed to reproduce a model. One thing that is also important, I think, to kind of demystify a little bit the complexity of LLMs is to understand that, like, the Llama team that worked actively, and I mean, hands-on coding and all that, this model did that for only 6 months, and were only these 5 person. So a team of 5 people for 6 months with enough compute were able to produce that. So when I see that, we need, GPT-4 text like 400 people, so massive, it's impossible to get to that level, it feels to me that probably the reality is in between. You probably need some consequent team and investment, but maybe not to the scale of what has been promoted so far. Thank you.
Thank you very much for the amazing talk. We have time for a few questions. One.
Hello. So I thank you for the nice talk. I really like the cost slide. So you mentioned A100s, 2,000 of them. Each one of these boards costs $10,000. So 2,000 such boards would cost 20 million just in hardware. So the barrier of entry is huge. My question would it be possible to do this with consumer level GPUs? So there's a graphic card from NVIDIA with pretty much the same compute, but 3 times less RAM on it. So is the training limited by compute, or is it limited by onboard memory? That would be my question.
Yeah, great question. So I'm not going to discuss should we use consumer, like hardware that is not supposed to be used, because I think that it would be illegal. But the core question is the RAM the limitation versus just the power of the GPUs? And yes, the memory is definitely a big bottleneck. The reason is that you need, at least for the bigger models, because the small one kind of fits in a 40 gig A100, for example. But if your model cannot fit in 1 GPU or 1 node, then you need to split it between nodes. So you need even more GPUs. So now comes the problem of interconnects. And so you need fast interconnects like InfiniBand and so on. So now you need a cluster. And InfiniBand is really hard to set because you need cables which are exactly the right size. So it's an additional cost of 10% on your data cluster, data center and so on. So it's not negligible. So there is really here a thing and a problem between if your GPUs are too cheap, then you need to put them in a data center that is not cheap, and so it kind of makes no sense. So I think that's a little bit where the thing is. So H100 has 80 gig, are faster. So probably here also is going to be quite interesting to see how they super improve things. But I would say in general, you want things with high RAMs, or else you have InfiniBand somewhere. But that's usually not always the case.